All right, this is the last topic in organic, and it's going to take me about 3 days and probably about a week's worth of time, but 3 actual days of notes to get through it. And it's really a topic that is absolutely one of the most advanced ones you're going to see in a college class. None of this is going to be on the AP exam. All right, organic. You're going to see it in organic, absolutely, and more likely than not, you're going to see it even later in organic, or not even early, where you're just going to learn the kind of stuff I've been teaching about simple naming and maybe some isomers and stuff like that. Mechanisms, we go into a lot of detail. I'm just going to give you 4 basic mechanisms that are going to illustrate different parts of the points about the mechanism. First thing, what is a mechanism? All right, well, up till now, I've just been giving you an overall equation. How that equation actually comes about. How you can take water and add it to an alkene and you actually get an alcohol. It doesn't just happen in one quick simple step most of the time. Most of the time, these things take multiple steps. And that's what a mechanism does. It describes a step-by-step progression of what happens in a reaction. Okay, a detailed, step-by-step description of how a reaction occurs. Not just what you get, and not just what you added together. And some of you may be wondering, why? What's the point? Why do I have to know this? Well, obviously, if you're not going to be a chemist, there isn't a whole lot of reason, but I am going to try to give you a couple of reasons why you might want to know these things, and why you're going to study them in organic anyway, whether you want to or not. All right? Because it seems like this would be something that only a real chemist would actually want to do, or need to know anything about. Certainly I won't need to know it as a doctor or as a pharmacist or any of the other things. Well, that's not true. All right. First of all, how it would help you in one way is that you know how you had like 25 reactions on that sheet, and I told you you're not going to get a sheet when you go to college. You're going to basically get you have to memorize all this stuff. Well, and that was 25 is not all the reactions you'll have to know. You'll have to know more than that. How the heck am I supposed to memorize all those things? Well, one of the ways. Many of those guys go on through the same mechanism. So even though it's a different reaction, you get alcohol here, you get an alkyl halide there, you actually are doing the same basic thing. A lot of those guys are similar. So that's one reason. It will help me to study, to understand, and to remember the actual reactions I'm doing, because many of them go by the same mechanism, or a very similar mechanism. So that's one reason why you might want to know that, even if you're not going to be a chemist or a research pharmacist who's actually going to care about this kind of stuff.
What about a writer?
If you're going to be a writer, I don't think you're going to need it very often. It's not going to come up.
All right.
It's not going to come up in most conversation or writing. People aren't going to stop you on the street and ask you about the free radical halogenation mechanism. It's not going to happen. However, if you're going to take organic chemistry in college, you're going to see these 4 mechanisms. I'll guarantee you that. And you won't see that. Organic is generally a second-year class. And this is usually not the first topic you're going to see. So you're talking about somewhere in the middle of your sophomore year, you're going to see this kind of stuff. This is pretty advanced stuff. All right, well, that's why you might want to know. Why does an actual chemist want to know? All right, well, there's a good reason for it. If I know the mechanism by which this guy produces a product, I can make a better product. I can make it cheaper. I can make it faster. I can make it better. I get more of it. That's the main reason. Okay. I can also here. Look at this. Look at this web of stuff. Look at all these different reactions that you can have. You really think you can memorize all those things separately? All right. A lot of those guys turning an alkene into these different things are going to go by the same mechanism. All right, and that will make it a heck of a lot easier to memorize the 40-some reactions that are on here. Okay, I only gave you 25. All right, and you didn't have to memorize them; you had a sheet with them. All right, but again, for a chemist, what would you most likely want to use this for? Well, knowing the mechanism, we can manipulate it. I could use this solvent instead of that solvent. I could heat it to this temperature. I could use this catalyst, and therefore get better or get more of the desired product faster or better. Improve my yield or improve my efficiency. All right, now again, that's not something that most of you are going to be doing ever. All right, unless you're going to go into industry, unless you're going to be a chemist or a research type of chemist, a research pharmacist or something like that, you're probably not going to have to deal with that stuff very often. You basically just do your job. All right, and most of you are looking, I would imagine, in the medical field where you're really not going to, except for knowing it through college, you're really not going to come up on a daily basis what the mechanisms are for these things. But trust me, you will see it in college, and part of the deal is getting through college to get to be what you want to be. All right, but for a real chemist, that's the reason they know it. And I'm going to show you some of that today when I go through this. If I know, for example, one of the first things I talk about with free radical halogenation, I find that the first step in that is breaking up a chlorine molecule. Well, if you remember in my equation, it had underneath the arrow heat and light for that. A particular wavelength of light happens to break chlorine the best. If I know that's the mechanism, I'm going to use that wavelength of light to break chlorine, make the reaction happen faster. All right, so that's the basic idea behind why we're going to talk about mechanisms. Now let's get to the first one, called free radical substitution. Okay, this is a great example because it illustrates a chain reaction mechanism. And you should see what a chain reaction is. This is a good example of that. It was the first example, the first mechanism I ever remember covering in college. And it has a lot of steps, more so than the other mechanisms we're going to see. And it's a chain reaction, which is the other ones are not. So there's a reason to study this guy. He's probably one of the most studied mechanisms. We talk about this one the most. You're guaranteed to see this one in college, probably the first one you'll talk about. All right? And it's used for a reaction that if you looked up on your sheet, you would see an alkane reacting with halogen is going to give you an alkyl halide. It was one of the first ones we did. The only one I think that came before that was combustion. We did combustion where we burned it, methane plus O2 yields CO2 in water. The very next one was this one. And it looked like this. The overall reaction looked like that. I think that you have it on your paper, right? Okay. Now here's the thing. This does not happen in one simple step. This actually happens, there's going to actually be 6 or 7 steps, possible even more than that. Not that they are productive. Sometimes they probably happen, but they don't really do anything. So there's a whole lot of things that can really happen to get this guy to give you that product. And there are 2 products. The 2 products are that and that. Now, I can draw this guy out 2 different ways. I want you to realize that. I'm going to draw in my first mechanism, I'm going to draw it written like this, so you can type it, basically. But, you know, we're used to seeing this, aren't we? Okay? In organic. So it could be written like that. And another way it can be written, believe it or not, is even with the Lewis structures. So like this. Like that. So that would be him. That would be him. This could be him. And why am I writing them all this way? Because it's going to turn out that those electrons are going to be important in the steps of the mechanism, what's happening to those. Now, before I begin this first one, I want you to realize that no one can prove a mechanism. You can't get a little video camera and videotape those electrons being moved from place to place. It just doesn't happen. It happens way too quickly, and it's way too small for you to ever see it. All these things are happening in microseconds. And we're talking about very, very small amount of time and very, very small things, like electrons. Not that you could see an electron anyway. All right? So we're just making indirect observations to be able to come up with what we think actually happens in a mechanism. You can't prove this to be the fact. Sometimes, and this is the case even today, you think, well, we know everything about science now. There are reactions that there's more than one possible mechanism that they can go through, and we don't know. We just don't know exactly which one. More than one fit the results, so you can't tell, because there's no video camera down there to tape this stuff. All right, let's look at the mechanism. First step is called the chain reaction mechanism. Well, the first thing has to be something that begins the chain reaction. All right, this is the actual mechanism, and that's called the chain initiating step. Okay, chain initiating step looks like that. You could write that to the side over there in your notes. Notice it requires heat and light to break up a chlorine molecule into a chlorine. Now that guy right there, you might think to yourself, so that's a chloride ion? Actually, he's not. He is called a free radical. I'm going to have the definition of free radical down at the bottom of your paper there, and I'm going to give it to you a little bit in a little bit. But that's actually called a free radical. Let me draw that same guy out for you. You don't do this, because it's on your next paper. I gave you 2 papers there. I have it drawn one way or another. But if I were to draw this guy, you all agree that he would look like that when he's drawn together. We've drawn Lewis structures like that before. He's sharing electrons. Everybody's got an octet. Everybody's happy. All right. If I were to break him up, I would get two chlorines that would look like this. It doesn't really matter where I put the unpaired electron here. I just put it down at the bottom. It doesn't really make any difference. The point is, I got two guys who are missing, seem to be missing an electron out of there. Now, they're not technically missing to make him a positive charge. It's just the fact that chlorine is diatomic for a reason. A chlorine atom with that one unpaired electron is not happy. We know that. Things that aren't filled, especially things that are that close to having an octet, not happy. An unpaired electron on anybody is going to spell trouble. It means that he's going to be like looking for an electron with anybody he can get it from. These guys are called free radicals, things with unpaired electrons on them. You've heard about free radicals. It's in the cosmetic industry. It's in the health and beauty industry. It's talking about free radicals are what causes aging. And you take these antioxidants to get rid of the free radicals and all these other things. If you follow any of current kind of medicine, current kind of trends in vitamins and in health and beauty stuff, they'll always use the word free radicals. All right? Because they do gobble up. They're very reactive elements. They're going to react with almost anything, and that's what does cause some of the aging. Now, I don't buy into all of the, it's just another catchphrase. We've talked about this before. There's a lot of garbage science out there. Whether or not your vitamins, your antioxidants are going to take care of free radicals and prevent aging, I would doubt it. But it is. Have you heard that word before? I'm assuming you've heard it. Right? Okay. All right, so that's your first step. That's a chain initiating step, and it's a chain initiating step because he creates this Pac-Man-like molecule that wants to go gobble up something, gobble up an electron to make him happy. When he does that, the only place he can get it from is some other compound. I'm going to draw a beaker of what's going on in here and then ask you a question about it, okay? Remember, this is my equation in this beaker. You ready? Don't write this down. I just want you to see this. Oh, that's interesting. There, there. Do the same exact thing, but this time it'll work. No, it's in green. For no reason. I have not used green all year. No, that's not true. But I haven't used green all day. Yeah, it's in green. Okay. Remember, this is my general formula. Okay? I'm taking those two things and I'm reacting them together, right? So if I put in a mole of methane and a mole of chlorine gas into my beaker, here's my beaker. Methane and chlorine gas are both gases. They're both gases. So here's my methane molecule. I'll make him in blue. I got a whole bunch of them in the beaker, floating around. And I've got a whole bunch of, we'll make our chlorines red. I'd make them green, but you can't see them as well. Okay. So I've got the same, let's assume I have the same amount of both in here. Chlorine and methane, if you have, I don't know if I do, it doesn't matter. In the beginning, they're sitting there. They're just kind of hanging out. There's no heat, there's no light. There's nothing to break that first chlorine molecule. Here comes the light. Light comes in. And it breaks, bam, cleaves that first chlorine molecule. Now instead of chlorine, I've got two chlorine free radicals. Okay? So I got these two guys who are out in the town looking for some action. And they're going to bang into somebody. They're going clubbing. They're looking for somebody to get it on with. Now, who can they run into? Well, they can run into another chlorine molecule. And that ain't going to do a whole lot. Because here, if I take a chlorine free radical and I bang him into a chlorine molecule, here's what will happen. Okay, let's take a look at this guy. Here's a chlorine free radical. And here's your chlorine molecule drawn out. Okay? What he'll do, he'll take, okay, I'll take this guy. I'll take this one with his, and I'll combine with that guy, right? And that will give me a chlorine molecule again. But another chlorine free radical. So what's the point of that? There isn't any. There's no, I mean, does it happen? Is it a chance? Is it most likely that this guy is going to bang into some other chlorine molecule? Sure. But it doesn't do anything. It just gives you the same two guys over again. However, what can he hit, pull something off of?
Hydrogen.
Not hydrogen. There's not hydrogen in there. There's no hydrogen in there.
Or carbon.
Not carbon. You know what that word is called. Methane. Exactly.
Methane.
All right. There's methane in there. So let's see what happens when he bangs into a methane. Because the chances are, he really, in the beginning, the first chlorine that's broken up can only hit a methane or another chlorine, right? Okay, so let's see what happens in that case. That's called a chain propagating step, where the methane molecule hits a chlorine-free radical, and what does it look like that chlorine-free radical does? What does he do? Well, yeah, he does. Actually, no, he does not switch places with the hydrogen. He steals a hydrogen. He steals a hydrogen. Let me show you that drawn out with electron dots, which you'll see on your second paper there. If I were to look at the electron dots, it would look kind of like this. This is the worst board. Okay? Right? There's my methane, and here's my chlorine. I'll draw him in red. What does he take? He takes a hydrogen and one of his electrons, right? And he puts them over there, and I'll get an HCl. What does that leave for him? He left one of those electrons behind, didn't he? So carbon, that methane is now a methyl free radical. He's now a methyl free radical. And guess what? He's just as reactive as that chlorine free radical was, because he's got that unpaired electron. He needs to get an electron. He's like a Pac-Man. It's a chain reaction. We made this guy, who is, by the way, one of the two products, but I've also regenerated him, who is now free to bang into anybody else in that beaker, right? Who else is in that beaker? Well, that's interesting. I know he's in there. Hold on. Who else is in that beaker? Let's take a look. Well, yeah. Now that I've got a CH3, he can bang into chlorine, or he can bang into a CH4. If he bangs into a CH4, what's he going to do? Pull off an H? Not going to do much. But if he hits a chlorine, that's what we're going to look at now. Okay? What will happen if he hits a chlorine? This is like sex ed. Sure. What's going to happen if he hits a chlorine? What does he pull off? He takes a chlorine from the two that were there, but leaves behind a chlorine-free radical. What have we done? We've regenerated yet another chlorine. Every one of these steps, that's why they're called the chain propagating steps. They keep regenerating free radicals. But let me remind you of something as I write something down at the bottom here. Take a look. You don't need to draw this because it's already at the top of your paper. Remember, it's amazing. Remember, when I take the original equation, look like this. Do you remember that? If you look above on your paper, that's the original equation. Notice each of these chain propagating steps produced a product. Okay? This product and this product. See that? This product, HCl, was produced up here. This product, CH3Cl, was produced right there. So in the process of making my final product, he was also regenerating free radicals that can go back and keep reacting and making more product. And this will continue for a very long time. But eventually, let's think about this. Eventually, what will happen? As these free radicals gobble up each of these guys, and they're gone, and they're gone, he's gone, he's gone, he's gone. You know, in the beginning, odds were very good that first chlorine free radical that was formed when I broke up chlorine, odds were very good he was going to bang into a methane or another chlorine. But they all got used up now. What now can happen that would bring an end to this process? What might they bang into that would bring an end? Chain terminating steps that would not result in a free radical. What do you think? What can they bang into? other free radicals. If a chlorine free radical bangs into another chlorine, as unlikely as that is in the beginning, when we've only created our first one, and there's a whole beaker full of other crap around there, as unlikely as it is in the beginning, eventually it happens. And that brings the whole thing to an end. You see? Because I don't make a free radical when at this point. What other free radicals could bang into each other? The CH3, the methyl free radical could bang into the chlorine free radical. Or, there's one more possibility. 2 CH3s. And that brings me back to how I told you a little while ago. I can't prove these reactions are exactly what happens, but I have indirect evidence that this is what happens. And all the mechanisms I'm going to talk to you about, we believe this is what happens. We don't know it, we can't prove it, but we believe it because of things like this, right there. That's a crazy idea. Whoever thought? If I told you, if anybody, I give you $1 million for the next Nobel Prize for having predicted back when we originally did this a month ago. Who in their right mind would have said CH4 plus Cl2, that's on the sheet, on your test a month ago? And you would have said, oh yeah, well, you know, you're going to get CH3, Cl, and HCl, and I got to get a little bit of C2H6 because of this. Nobody would have guessed you would have gotten some ethane from reacting methane with chlorine, right? No one was going to write this down. There's not one person who made that mistake because it doesn't make any sense unless this is the mechanism by which it goes. This is a side reaction, a side product that you would get that happens. And we know that because it does happen. And so that's not proof, but it's evidence that it probably goes through this method, through this mechanism. Okay? You see what I'm saying there? All right. So, what kind of questions could I ask you about? I have a couple of things I want to do before I leave you go. What kind of questions could I ask you about this? Well, I could say, and I know I do this, and we have 2 worksheets on this stuff. You don't have to do this. Just listen and look up here. I could ask you, first of all, to box all of the free radicals that are in the first 3 reactions. So I put a box around him. I put a box around him, and him, and him, and him. Okay? Those would be all the free radicals in the first 3 reactions. I could ask you which of these reactions to circle the ones that produce a product. Does this produce a product? No. Does this one? Yes. Yeah, it produces that guy. So, he does. Does this guy produce a product? Yep, he produces that guy. Is that guy? No. That guy? Yes. That guy? Well, no, not a product that I expected, a side product. I could ask for which is a side product that's produced. I could say that. I could ask you to identify the steps. Now, a lot of you are going to say, well, that's easy. The steps are right in order. I mean, what if I don't put them in order? I'm going to do that in a few seconds. I can say, identify this as a chain initiating, chain propagating, and chain terminating step. How will you do that? Well, I want to show you right now how you do that. First off, by the way, you all have a definition, right, at the bottom of your paper. A free radical is a very reactive atom or group of atoms that has an unpaired electron. And you know why he's reactive. The octet rule, basically. Things want to be filled. Okay. Now, I wanted to show you real quickly. You have this paper on your second paper there. This is just drawn out with the electrons on it, showing what happens to the electrons for the same steps. So if I were to draw this, the step I had before as the chain initiating step, I would draw it like that. I would draw the chain propagating steps like this and the chain terminating steps like that. Now, if I mix them up like that on the test or on a worksheet, can we tell which is which? Let's see. I think you can if you just keep a couple of little things in mind. First of all, what do you think A is? Chain initiating, chain terminating, or chain propagating step? Terminating. A. Initiating. Nope. Chain terminating. Here's why. A chain terminating step is going to take free radicals and not generate a free radical on the other side. That's a chain terminating step, right? Let's take a look at D down here. What is that guy? Not a chain initiating. Nope. It already has a free radical. And it regenerates a free radical. So it's a chain propagating step. So that's what you're really looking for. For chain initiating steps, you're going to take a guy who doesn't have a free radical and make one. For a chain propagating step, you're going to have a free radical on both sides. Here's a free radical over here. Amazing. You draw like for 20 minutes, then it finally starts working. Here's your free radical over here. Here's another free radical on this side. That's a chain propagating step. What do you think this step is here? Yeah, because you're taking a free radical and another free radical, and you're making non-free radical. Yeah. What about this guy down here? Chain initiating step. I'm taking a non-free radical, it's just a chlorine molecule, and making 2 chlorine-free radicals from it. Got it? All right, so I could ask you to identify chain initiating, chain propagating, chain terminating steps. Which guys are the free radicals? Which guys produce product? Which are the side products? Got it? All right, good enough. And I will on the